This video is going to serve as some basic important reminders about integration. So you should keep this handy when you're integrating, just so you don't miss anything important. The first thing to remember about integration is that there is plus c. So whenever you have an indefinite integral or just a regular antiderivative, you must include the plus c because that describes the family of functions that solve the integral. With definite integrals, i.e. with limits, you don't have to do the plus c. If you just want to make it easier for yourself, always do the plus c, and then they'll cancel when you finish the definite integral. The second thing to remember about integration, let's say, for example, I have the integral of cosine of x dx. Okay, in your head, you cannot think about rules. Okay, because unlike taking derivatives, there really aren't rules for integration. The thing I like to think about is we have the answer, right? The answer is cosine. The question is, what function do I take the derivative of ddx of what is cosine? Well, what function do I take the derivative of to get cosine? And the answer is sine. And so therefore the antiderivative of cosine of x is sine of x, wait for it, plus c. So that's how you have to think of integration. It's really this process. Derivative of what is cosine. So let's just review the basic derivative rules and then see their integral parallels. This is my format. I'll just list off some derivative rules and then we'll go from there. So the first one, the derivative of a constant times x. So recall if you have the derivative of 3x or 2x or 8x, the derivative is just that constant. So going backwards, if I'm integrating a constant, I just put back the x. So think about it like the antiderivative of 3 is what function when I take the derivative of it gets me 3. It's just going to be 3x, and so I go backwards. So it's kx and then plus c. If I have the derivative of k times a function f of x, then really all I'm doing is pulling out the constant and keeping it there, and so I get k times f prime. It just stays there, which is nice. Likewise, if I have a constant times a function and I'm integrating it, wow, I'm really bad with these colors today. If I'm integrating, there we go. If I'm integrating a function, what I can do is I can take that constant out and just do the integral of the function and then multiply it back in. So it's a nice little trick. So if I have a constant out in front, basically you keep it there and you just do the integral as normal and then multiply the constant back in. Don't do any product rule stuff, that's just icky and gross. So yeah. If I take the derivative of a function plus or minus a function, it's just plus or minus the derivatives. Same thing with integrals. If I integrate the sum or difference, I'm losing my colors. If I integrate the sum or difference, these are not primes. If I integrate f plus or minus g, the answer is just the integral of f of x dx plus or minus the integral of g of x dx. So I can just split up integration using plus or minus. And then the last one for this page is that power rule. The derivative power rule, we bring down the power, and subtract. Going backwards, we do the opposite. If I'm integrating x to the n, I add 1, x to the n plus 1, divide by the new power, and then add my plus c at the end. And then there's everybody's favorite, the trig stuff. So basically, if I have the integral of sine of x, what function when I take the derivative of it gets me positive sine? Well, we're going to start with cosine, but be careful, the derivative of positive cosine is negative sine, so I need to throw in a negative here. So it's negative cosine of x plus c. The derivative of positive cosine, the antiderivative of positive cosine is just positive sine of x plus c. What function gives me secant squared? That would be tangent x plus c. What function gives me cosecant squared? Notice that this is positive. So the integral, or the function that gives me positive cosecant squared is negative cotangent of x plus c, because when I take that derivative of cotangent, I'll get the negative come out, which will cancel with this negative here. What derivative gives me secant tangent? That would be secant x plus c. And then here I'll have negative cosecant x plus c. So these are just the derivative rules backwards. This is basically how you can know them. Now, with derivatives, there were other rules like the product rule and the quotient rule and the chain rule. These don't have a direct correlation with integration. So, for example, the derivative rule for the product rule is just f prime g plus g prime f. Well, if I want to integrate two functions that are multiplied by each other, guess what? I can't do it. It's not the integral of g(f), and no, I can't do it. There are ways of doing this, but we're not going to learn them unless you're in Calc BC, then we'll do it in Chapter 8. But for the most part, if you see things like this, there is a different way to do it. There is no integration product rule, basically. So that might be good for some of you, but maybe not as satisfying for others. Treat it as you will, but yeah. What this does mean, however, is that we have to be very, very careful when we are integrating. For example, let's say I want to do the integral of x plus 1 over x squared dx. You might be tempted to pull out your new power rule and put it in use and be like, alright, the integral of x is x squared over 2. Cool. The integral of 1 is x, and the integral of x squared is, wait for it, x cubed over 3. I just used the power rule. Oh yeah, and also there's that like plus c. Unfortunately, my kitten is dead because you've killed it 1, 2, 3 times, and that is sad. You cannot integrate like this. You have to rewrite it so that it matches one of your rules, like exactly matches. Most of the time that's going to involve making fractions or rewriting trig stuff so that it comes out to be like a single trig function. So the way that we do that with this example is rewrite it as two separate fractions. If I have one denominator, I can split these two things up into two separate fractions. X over x squared plus 1 over x squared. I still can't integrate this because it's not one of the rules. I can, however, rewrite these using a different power. X over x squared is the same as 1 over x, which is the same as x to the negative 1. And I just realized that we don't know how to do this yet anyway. So I'm going to change the problem. Careful, stay with me here. We're going to do x squared on top. Squared, squared. So this becomes 1 instead of x to the negative 1. Yeah, you'll see why in a second. Okay, so I'm going to be integrating 1 plus, and then 1 over x squared, I have to rewrite this in order to integrate it, just like I had to rewrite it when I took the derivative. It's x to the negative 2, and then I have my dx. Alright, well the integral of 1, I can really think of this as x to the 0, or I can say, well it's just x, because I put the x back. So it's x, and then plus, alright, x to the negative 2. Let's use that reverse power rule. So I'm going to add 1, and so I have x to the negative 2 plus 1, which is negative 1, divided by, dividing by the new power, that's easy. It's just divided by negative 1. I have my plus c, and I'm going to rewrite it a little bit so it's in a nicer format. It's going to be x, that negative 1 is going to give me a minus, and then 1 over x plus c. And that is my antiderivative. Notice, okay, so when I redid that problem, I had to rewrite it, because if I try to use the power rule on x to the negative 1, bad things happen, because, x negative 1. Let's say I add 1. Cool. Then I get x to the 0, and then remember that I divide by the new power